Hello everyone. Today I'm going to talk about natural language processing with distributed learning. I'm Jiageng Liu from Math Department and Tian Weixing is from Electrical Engineering Department. This talk is dedicated as part of the final project for CS269, Natural Language Processing with Machine Learning. So why do we do distributed learning? There are two major concerns. The first is the cost. Nowadays, there are billions of devices, from cell phones to laptops and even the watches you wear every day, that constantly collect data from texts to user behaviors and that kind of thing. And it is really cost efficient to maintain a data center that stores and processes as much as 100,000 terabytes of such data per day. Another thing is a privacy issue. Sometimes people simply do not want to upload their data onto the server. For example, Google DeepMind has some trouble because it broke the UK privacy law by downloading some patients' personal data from the National Health Service database. I want to introduce three different strategies to solve the problem. The first one is called federated learning. In federated learning, each user will download the model from the server in step A and updates the local model with its data it collects from time to time. And then after a lot of users have updated their own models, the server will collect all these updates onto the server. And all these updates will reach a consensus update, and the server will push this update onto the model. So in this case, users can go online anytime, anywhere to join the computation, and only primary parameter update is involved, so there is no privacy issue like data transfer. The second strategy I want to introduce is the diffusion learning. In this case, we get rid of the server altogether, and there is no need for synchronization between all these models. So instead of using a server, all the computing nodes will only communicate with its own neighbors to communicate the parameter updates. For example, the node 3 here will update its own model and pushes update to the 3 neighbors that it can communicate with. And this model, this node will communicate with this one and this one too. So in this case, the information kind of diffuses along the network from this one to this one, even if they are not directly connected. And we can reach consensus as well as optimality altogether. And another thing is, in this case, we can have arbitrary network structure, and there is no privacy issue. Thirdly, I want to introduce incremental learning. In this case, it's still a decentralized model like diffusion learning. However, instead of arbitrary network topology, we predefine a cyclic trajectory, for example, from 1 through 6 in this case. And after, for example, node 1 update its own model, it will push its update onto node 2. And node 2 will kind of transfer the update to node 3, and so on and so on, so that all the nodes in the network in one iteration will receive the updates that use the data collected by node 1. And in this case, we can save a lot of communication compared to previous models because the cyclic structure is the simplest structure you can have on the network. However, we really need a reliable network for this model to work because, for example, if the link between 3 and 4 breaks, then the network will fail. So we adapt the 3 strategies onto a simple neural network to see the performance. As you can see, in terms of computation, the blue line is the best, which stands for the federated averaging strategy, and the black line, which stands for incremental strategy, is the worst. In terms of communication, incremental strategy is the best, while the federated averaging strategy is the worst, but not so bad as in this case. So you can see that it doesn't even reach the 0.1 loss value in our experiment. So we decided that the federated averaging strategy is more realistic and more useful. So we further apply the strategy onto a classical natural language processing task called word-to-vec. So in word-to-vec model, we map all the words in the vocabulary to a continuous high-dimensional space. And we use the inner product between vectors to find the probability of their co-occurrence. And we use the softmax to link the inner product to the probability of the co-occurrence, and use the stochastic gradient descent to go over a lot of text data and see the frequency of their co-occurrence and adjust the positions of their vectors. So we adapt this strategy of federated learning onto the word-to-vec model. So you can see we use 5 workers on a Titan X GPU with TensorFlow, and all the workers have same amount of data. So from the loss curve here, you can see that the red line, which stands for the federated cluster, is about 3 times faster than the single machine word-to-vec in terms of loss value. And from the log loss value, you can see that this advantage, that is the gap between them, has been kept along the way until the loss function reaches a very low value. And we introduce some reference here. If you're interested in all the 3 strategies, you can implement them on yourself and see whether it's useful on other different models like machine translation or other like information extraction applications. Thank you so much for listening.